Geometrical representation of cubic polynomials. First, we looked at linear polynomials, which are polynomials of degree 1. We observed that a linear polynomial always has exactly 1 zero. Next, we moved up to quadratic polynomials, which are of degree 2. In this case, we learned that a quadratic polynomial can have at most 2 zeros, meaning it could have 2, or it might have fewer, but never more. Now, having understood how degree 1 and degree 2 polynomials behave, we are going to extend this very same logic to a higher level. Today, we will explore the geometrical representation of cubic polynomials, where the degree is 3, and see how many zeros we can expect to find. Welcome, everyone. Before we dive into our new topic today, let's take a moment to quickly recap what we have already mastered in our previous lessons. Understanding cubic polynomials. Now that we've recalled how linear and quadratic polynomials behave, let's dive into the core of today's lesson, understanding cubic polynomials. First, by definition, a cubic polynomial is simply a polynomial where the highest power, or the degree, is 3. To work with these mathematically, we use a general form, which we write as p of x equals a times x cubed plus b times x squared plus c times x plus d. It is very important to note the condition that a cannot be equal to 0. If a were 0, the x cubed term would disappear, and we'd be back to a quadratic polynomial instead. Now, let's shift our focus from the algebra to the geometry. If you were to plot this equation on a coordinate plane, you wouldn't see a straight line like we did with linear equations, nor a simple U-shaped parabola. Instead, the graph of a cubic polynomial is a smooth, continuous curve that typically resembles an S shape. The reason for this unique shape is that, unlike a straight line or a parabola, a cubic curve has the flexibility to change direction twice, meaning it can have a peak and a valley. Because of these two changes in direction, the curve has the ability to weave back and forth across the horizontal axis. As we will see in the upcoming examples, this flexibility is exactly what allows the graph to cross the x-axis at multiple different points, giving us anywhere from 1 to 3 possible zeros. The relationship between the graph and zeros. As we established in our previous lessons with linear and quadratic functions, the zeros of a polynomial, which we call p of x, are simply the x-coordinates of the points where the graph of y equals p of x intersects or touches the x-axis. In other words, whenever the curve meets the horizontal axis, those specific x values are our zeros. However, as we move into cubic polynomials, something interesting happens. Because the cubic curve has the ability to change direction twice, the number of these intersection points is not fixed. As you will see in the upcoming examples, the number of times the graph meets the x-axis can actually vary. Now that we understand what a cubic polynomial looks like and its characteristic S shape, let's connect that shape back to the concept of zeros. Example 1, a polynomial with 3 distinct zeros. Now that we understand the general shape of a cubic curve, let's move from theory to practice with our first concrete example. On this slide, we are looking at a polynomial where p of x equals x cubed minus 4x. To understand how this looks on a graph, we'll perform a step-by-step analysis, starting with the algebraic solution. To find the zeros, which, as we discussed in the previous slides, are the points where the graph meets the x-axis, we simply set the entire polynomial to 0. So, we start with x cubed minus 4x equals 0. Next, we need to simplify this equation using factorization. Looking at the terms, we can see that x is a common factor in both parts of the expression. When we factor out the x, we are left with x multiplied by the quantity x squared minus 4, which equals 0. We can actually take this a step further. Notice that the expression inside the parentheses, x squared minus 4, is a difference of squares. Using our algebraic identity, we can factor x squared minus 4 into the product of x minus 2 and x plus 2. Now our fully factored equation looks like this: x times the quantity x minus 2 times the quantity x plus 2, all equals 0. This brings us to the most important part, Identifying the zeros. For this product to equal 0, any one of these three factors must be 0. This gives us three distinct solutions: x equals 0, x equals 2, and x equals -2. Finally, let's connect this back to the geometry. If we were to plot this curve on a coordinate plane, we would see the graph crossing the x-axis at exactly three distinct points. Specifically, these are the points -2, 0, 0, 0, and 2, 0. This perfectly illustrates the concept we are about to explore in the next examples, where we will see how the number of intersections can change. Example 2. A polynomial with 1 0. Now that we've seen how a cubic polynomial can have three distinct zeros in our first example, let's look at a different scenario where the number of zeros is reduced. On this slide, we are considering the polynomial p of x equals x cubed. Let's walk through the step-by-step analysis to see what's happening here. First, for our algebraic solution, we follow the same rule we've used throughout this lesson. We set p of x equal to 0. This gives us the equation x cubed equals 0. When we move to identifying the zeros, we ask ourselves, what value of x, when multiplied by itself 3 times, results in 0? The only possible answer is x equals 0. Now, let's connect this back to the geometry, as we have been doing. If we were to plot the graph of y equals x cubed, we would see that the curve passes through the origin, which is the point 0, 0. However, unlike the previous example where the curve crossed the axis multiple times, this curve simply passes through the origin and then continues to rise upward, never dipping back down to touch or cross the x-axis again. Because it only meets the axis at that single point, we conclude that this specific polynomial has only 1 0. This sets us up perfectly for our next example, where we will see a case that sits right in the middle, a polynomial with exactly 2 zeros. Example 3, a polynomial with 2 zeros. Now, let's look at our third example, which is a bit different from the previous two. In example 1, we saw 3 distinct zeros, and in example 2, we saw only 1. This time, let's consider the polynomial p of x equals x cubed minus x squared. Let's walk through the step-by-step analysis together to see what's happening here. First, for our algebraic solution, we start by setting the entire polynomial to 0, so x cubed minus x squared equals 0. To solve this, we need to use factorization. If you look closely at both terms, you'll notice they both share a common factor of x squared. So, we can factor that out, which leaves us with x squared, multiplied by the quantity x minus 1, all equal to 0. Now, from this factored form, we can identify our zeros. For the equation to equal 0, either x squared must be 0, or the quantity x minus 1 must be 0. This gives us x equals 0 and x equals 1. Notice that because we have x squared, the value of 0 actually occurs twice. We call this a repeated root. Finally, let's look at the geometric interpretation. When we plot this on a coordinate plane, the curve meets the x-axis at the points 0, 0, and 1, 0. This is a crucial observation, even though we are dealing with a cubic polynomial, which, as we've discussed, has a degree of 3, the curve only meets the x-axis at 2 distinct points. This perfectly illustrates that the number of zeros can be less than the degree of the polynomial. This leads us nicely into our next slide, where I'll use a real-world analogy to help you visualize this concept even more clearly. Real-world analogy. Now, before we wrap up with our final conclusions, I want to step away from the abstract equations for a moment and look at a real-world analogy to help you visualize what we've been discussing. Imagine you are standing beside a roller coaster track, looking at it from the side. As the coaster moves along, the track might climb up a hill, dip down into a valley, and then rise again. This undulating motion is very similar to the S shape of the cubic curves we saw in our previous examples. Now, let's apply some mathematical thinking to this scene. If we imagine the x-axis represents the ground level, then the specific points where the track is exactly at ground level, meaning it touches or crosses the earth, are what we call our zeros. Just like the different polynomials we analyzed in the last few slides, the design of this track can vary. Depending on how the coaster is built, the track might touch the ground only once, it might touch it twice, or it might dip below and come back up to touch it 3 times. However, there is a mathematical limit here. If this track follows a cubic mathematical path, it is physically impossible for it to touch the ground more than 3 times. This perfectly illustrates the rule we are about to summarize. While the number of zeros can vary, it will never exceed the degree of the polynomial. Conclusion: the general rule for degree 3. Now, let's bring everything we have discussed today together to form a final conclusion. If we look back at the 3 specific examples we just analyzed, where we saw a polynomial with 3 distinct zeros, one with only a single zero, and one where the curve touched the axis to give us 2 zeros, a clear pattern emerges. We can see that a cubic polynomial is flexible. It can have 1, 2, or 3 zeros depending on how the curve is positioned. However, there is a strict limit. Based on the mathematical properties of a degree 3 polynomial, the curve can never cross or touch the x-axis more than 3 times. Therefore, we can arrive at our fundamental rule. A polynomial of degree 3 has at most 3 zeros. Keep that phrase, at most, in mind, as it is the most important part of this rule. Key takeaways. First, remember that the defining characteristic of a cubic polynomial is that it is of degree 3. Second, we must keep our focus on the geometry of the graph. As we discussed when looking at our various examples, the zeros are simply the x-coordinates of the points where the graph either intersects or touches the x-axis. Third, based on the 3 different examples we analyzed, where we saw 1, 2, and 3 zeros respectively, we can conclude that a cubic polynomial can have a minimum of 1 and a maximum of 3 real zeros. Finally, I want to emphasize the importance of the phrase, at most 3. This is a crucial distinction in mathematics. It means that while the number of zeros can be 1, 2, or 3, it can never be 4 or more. All right, class, we have reached the end of our lesson, so let's take a moment to consolidate everything we have learned today. This slide summarizes our key takeaways. As we move to our final slide, I will highlight a few common pitfalls to avoid so you don't lose marks on this concept in your exams. Common mistakes. First, let's talk about a very common conceptual error: confusing the term exactly with at most. Because we have just learned that a cubic polynomial is of degree 3, many students mistakenly assume that it must always have exactly 3 zeros. However, as we saw in our previous examples, specifically in example 2 where we only had 1 zero and example 3 where we had 2, the number of zeros can vary. Remember, the degree of the polynomial tells you the maximum possible number of zeros, not a fixed requirement. It sets the upper limit, but it doesn't dictate that the polynomial must hit that limit every single time. Second, be very careful when interpreting graphs. A common mistake is to look at the peaks and valleys, what we call the turning points, and mistakenly count them as zeros. While these points are important for the shape of the curve, they are not zeros unless they happen to lie directly on the horizontal axis. Always keep your eyes focused on the x-axis. As we have emphasized throughout this session, only the specific points where the graph actually touches or crosses the x-axis are considered zeros. Now, as we wrap up our lesson, I want to pause and highlight a few common pitfalls that students often encounter when studying cubic polynomials. It is crucial to address these now so you can avoid them in your exams. If you keep these distinctions in mind, you will have a much stronger grasp of the geometric representation of these polynomials. Great job today!